What's it look like it's doing? Finish putting it in? Kind of doing one of these. And you see that they're kind of getting closer and closer to being kind of the same thing. The one that is furthest away, of course, is this one. This is just a horizontal line. This is a 1.
Yeah.
And we stop here. How are we doing? Would you please state the geometric series theorem, the test, the geometric series? Figure it out. I can't believe they paid me to do this. This is awesome. Remember, our goal is to find a function and then be able to translate it into a polynomial approximation. That's our goal today.
Thank you. Sorry for having to go back to you. You know physiology. Rude. I switched over. I was Rockstar for a long, long time. Have you tried this one? Yeah, I was Rockstar. Huh? Don't you dare. Don't you dare. There's some on my lens.
Basically, it says if r, as long as the absolute value of r is less than 1, then it's going to converge to the first term over 1 plus that common ratio. We proved this. I actually derived this from scratch, however long ago. Like we started with an actual geometric series, and we came with all these formulas, and what if n goes to infinity, and the whole deal.
1 plus?
It's divergent in other ways, right? I'm going to rewrite this. Instead of r, I'm going to call it x. Why not? And I'm going to let my first term be a 1.
He's in sandals. He's in a good mood.
You don't know what that means yet. But we now have a function of x that can be rewritten as a polynomial. This function can be represented by this power series exactly like this, under which conditions of x? As long as x is between -1 and 1. Would you please graph this on the next one down? 1 over parenthesis 1 minus x. Make sure you put parentheses around that denominator, it won't work otherwise. You can make the line thicker.
Oh my goodness.
You see the polynomials are getting closer and closer to that function the further out you go? a polynomial representation for a bunch of different types of functions. We're going to focus on these types of functions today. Next time will be all about more familiar functions like sine, cosine, inverse tangent, natural log, e to the x, all those type of things. Now, again, you don't know what a big deal this is yet, but today we're going to make a huge deal out of this. So here we go. Not as impressive as 50 feet. Come on.
It's Thursday.
Alright. So, it has to exactly follow this because, in fact, we proved this before. I actually showed you where this came from. That's why this works. If it's not minus, it's not this. We're going to have to force the condition. So I'd like to do this. Our goal today is to... So our goal right now is to find a polynomial representation, or power series representation for a function. This is a little different than that one. I'm claiming that this polynomial, this power series, exactly converges here. Now you could run the root test or ratio test and figure out its kind of interval convergence. Not as interested in that for this particular lecture, but all of these that we create, we can figure out when it is convergent, when it isn't, using root test, ratio test. We okay? So if I take the functions 1 plus x squared plus x to the 4th plus x to the 6th plus x to the 8th plus x to the 10th, it's going to very closely imitate the function 1 over 1 minus x squared. Whatever that looks like. Now, if you think back to your pre-calc days, graphing this was terrible. You had asymptotes, you had two asymptotes, right? You have to factor that, one at 1, one at negative 1. Horizontal asymptote at 0. It got messy. I'd rather deal with a polynomial that closely resembles it than not. For whatever interval. Again, please note, we are only dealing with centered at the origin at this point. We will be deviating eventually. Okay, let's try another one. Notice I still have the minus, we're good. We'll handle plus here in a second. Try to come up with a power series representation for this particular function. Wouldn't share with a neighbor.
It would just be 5x to the end. Yeah. Yeah, that's what I was imagining it would be.
I'm claiming that this power series representation mimics this and becomes this over a certain interval. And again, we could figure out what that interval is. Questions? Do you see it's a polynomial? Yes.
When you say it mimics it over a certain interval, how far off can it be when it starts to diverge? Or what is technically happening when it diverges?
Then this no longer represents this. This represents this only on the interval of convergence.
All right, I lost you there.
That was the answer.
Right, but I'm trying to think graphically, how does it start to?
Throw it in the graph. Yeah, like do this up to like n equals 6 or something, and then see what happens on the big graph. So it's going to be mimicking it very closely, and then the function's going to take off somewhere, and this is going to be doing something. This is going to be going asymptotic or something.
Okay.
How are we doing? Let's try another one. Yes. There is a pattern, yes. 1 over 1 minus blah becomes blah to the n power. That's technical. Start to see the pattern a little bit? Let's try this one. This is a little different. It's kind of the same, but it's not. But I could do this. I know. Yes.
Is it necessary or just beneficial to write it that way? As opposed to like negative x and
We have to force it to be exactly this condition. 1 over 1 minus blah. Blah in this case is negative x.
right. I'm not saying the negative x, but you separated the negative 1 from the x.
It has to be 1 minus something.
No, you start.
Yeah.
Very final.
Oh, we want to always break it down like that.
Okay.
It makes it easier if you want to run the ratio test or the root test. We okay? Please find a power series representation of 1 over 1 plus x squared.
So it's just giving negative 1 to the nth x squared to the 2n.
We doing okay? What's the integral of that original function?
Tan,
1 over 1 plus x squared. What's the integral of that?
inverse tan.
How are we doing with this? Two over 1 plus 1/2 x. Just factor the 2 out here. It's not a 1 up here like it needs to be. It's something other than 1. So we can just factor it out. In fact, I could have rewritten this like this. One more step. Trying to figure out what I did.
Oh. I'm kidding.
The 2 cancels out with the 2 in the bottom. Kind of thing. Oh wait, no wait.
Yeah, I was like, how can it be 2 and minus 1 if it cancels
You
out?
make the 2 with the negative exponent, so it goes to the bottom, and then 2 times 2 to the first, I think, and then you know how they add each other or something. Oh wait, no. 2's in the bottom, 2's in the
I'd
top.
like to point out all of this discussion is about a pre-algebra topic. So, right?
That's what you were trying to say.
Yeah.
So if you bring that down, you okay?
That hurt.
We're okay.
That was rude.
Again, our goal is to force this condition. That is our goal. I'll hold your hand all day today, but you gotta hold on. We're climbing a mountain today. So what's wrong with this one? The 4, right? It's in the way. Let's do this.
1/4.
This is where algebra is really going to kick everyone's ass.
Oh yeah.
And he's got a step there. This one, yeah.
see how we're kind of forcing this condition every time? Sometimes you have to get a little creative. Any questions? So again, I want you to visualize this is a polynomial that's representing this function. Now there's a vertical asymptote at 4/3, right? There's a horizontal asymptote at 0, y equals 0. So we've seen this graph before. This is not a new graph. We're saying we can represent it with a polynomial for certain values of x. How do we know which values of x? That's what we spent all last time doing. Figure out which values of x we're allowed to use, which ones we're not. We try to look kind of like this. I'll let you play with it.